Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hello, students. So we have studied about the qualitative analysis of organic compounds. So in qualitative analysis, basically we try to find out which elements are present in the given organic compound. So which are the elements? If there is an organic compound, it means it will definitely contain carbon and hydrogen. If if there is any possibility of the presence of any other heteroatoms like oxygen, phosphorus, any halogen, chlorine, bromine, iodine, phosphorus, oxygen, etc. So this is what to find out what are the elements that are in an organic compound is what we call the qualitative analysis. And about the qualitative analysis we have already studied in our last class. Particularly what we see if we take a small amount of organic compound and if we heat it with the copper oxide, and after heating it with the copper oxide, we see that the carbon present in the organic compound is converted to CO2 and hydrogen present in the organic compound is converted to H2O. And with that CO2 we can detect using this select line because it forms calcium carbonate, and so calcium carbonate is white in color, and that white turbidity, if you see in the solution forming of white turbidity, it confirms that the CO2 is there into the solution, and that CO2 has come from the carbon that is present in the organic compound. And the water we detect using copper sulfate. Anhydrous copper sulfate we use, and anhydrous copper sulfate, when it absorbs water, it forms crystals, and the crystals that appears to be blue in color. So, and if then we see to find out to understand whether the other compound or other elements are there in or not in the organic compound, we resort to Lassen's test. And that Lassen's test we form sodium fusion extract. We take the organic compound in the distilled water, and then we heat it uh, and use in presence of sodium. So we take sodium into the organic compound in to water, distilled water, and then sodium into it, and then this is what, and we heat it. After a certain time, we see the formation of sodium fusion extract. A solution will be formed. Organic compound will be dissolved, and a solution will be formed that we call the sodium fusion extract. And using that sodium fusion extract, we try to detect the presence of other elements. And other elements for nitrogen, if the nitrogen is there, then the sodium fusion extract cyanide will be formed, and cyanide is detected with the Prussian color, the Prussian blue color, when iron Fe2 plus is added to the solution. Fe2 plus is ferrous sulfate is added to the solution. We see the Prussian blue color, and Prussian blue color confirms the formation of cyanide in the sodium fusion extract, and that cyanide has come from the carbon and nitrogen that are present in the organic compound. For the test of sulfur, we use lead sulfide, and in the sodium fusion extract, if you use lead sulfide, not lead sulfide, we use lead acetate, and the lead acetate forms lead sulfide, which is black in color, and a black precipitate when it forms, it means it confirms the sulfide is there into the solution. There is another test for detecting sulfide, and that is what we call the sodium nitroprusside test. To the sodium fusion extract, we take out a small volume of it into a test tube, and we add sodium nitroprusside. And this is Na2FeCN5NO is called sodium nitroprusside. And nitroprusside it gives a violet color, and this violet color confirms that the sulfide is present there. If sulfide is not there, and this compound also not only sulfide, it also contains nitrogen, then a thiocyanate ion is formed in the sodium fusion extract, and this thiocyanate ion, it forms a blood red compound, this ferric thiocyanate. This complex it forms, which is red in color, and it confirms that this compound contains sulfur and nitrogen both. And then test of halogen we do, and to testing halogen, the halogens will be converted into the halide ions, and these halide ions, if you add silver nitrate, we know silver nitrate, with addition of silver nitrate, we see the formation of AgX, chloride, bromide, iodide, they form precipitate. This is just by looking at the difference in the color and the solubility of this precipitate in ammonium hydroxide, we did find out which anion is there, which heteroatom is there, which halide is there, whether it is fluoride, bromide, or iodide. In details, I have already explained it how content is. To test phosphorus qualitatively, what we do, we oxidize the compound. In the presence, we take sodium peroxide to oxidize the organic compound, and we oxidize it. And with the oxidation, we see the formation of sodium phosphate. When sodium phosphate reacts with HNO3, so we add HNO3 to it, and as it forms phosphoric acid, and when phosphoric acid reacts with ammonia and ammonium molybdate, it forms ammonium phosphomolybdate. This is of this forms precipitate, and the formation of this precipitate ammonium phosphomolybdate confirms that the compound contains phosphorus. Then I also started this quantitative analysis, and quantitative analysis is important to find out in what percentage a given element is there in the organic compound, and what percentage means in what mass percentage. And once you know the mass percentage of all the elements that are present in the organic compound, you can easily find out the empirical formula, and then from the empirical formula and vector density, you can find out the molecular formula of the compound, and from the molecular formula you can also gauge the structure of the compound. And if there are only issue is if there are isotopes, formation of isotopes of that compound, in that case we also do certain analysis and we confirm the exact structure of a given compound. So for carbon and hydrogen, quantitative analysis of carbon and hydrogen we have already seen. So we take a combustion tube, we take the organic compound in the combustion tube, and it passes dry oxygen into it, and we heat this compound. In the presence of dry oxygen, we take dry oxygen so that the oxygen do not contain any water vapor. So dry oxygen means another and other gases as well. So once we pass the dry oxygen into it, the oxygen will now react with this organic compound, and it will react with particularly oxidized carbon and hydrogen present in the organic compound to CO2 and H2O, and it is passes through it, and the CO H2O that formed water, that is formed water vapor formed, is absorbed by calcium hydrous calcium chloride, and the increase in mass of the anhydrous calcium chloride will tell us what amount of water is absorbed here, and that's why we get the amount of water that is absorbed, and now the leftover the gases, the gaseous mixture after this will passes over another U tube which contains potassium hydroxide solution, and this potassium hydroxide will absorb carbon dioxide formed during this combustion of the organic compound, and the carbon dioxide it will form actually K2CO3, and that with the increase in the mass of this KOH solution, just measuring that how much mass of this KOH solution has increased, one can also understand what amount of carbon dioxide is absorbed here, and from the amounts of carbon dioxide and oxide and water, one can find out the percentage of carbon and percentage of hydrogen present in the organic compound, and the formula that we have obtained is for the percentage of carbon 12 into M2 into 100 divided by 44 4 into M percentage. This is what we get as a percentage of carbon. Here M2 is the mass of CO2 that we get that gets absorbed in KOH solution. This is the mass of CO2. This M is the mass of the sample that we have taken, and rest of the other terms that these are just numbers, and you know this. Please remember M2 here is the mass of CO2 that is absorbed here in KOH solution present in this Q tube, and M is the mass of the sample that we have taken. Then the percentage of hydrogen we can obtain as 2 into M1 into 100 divided by 18 into M. Here M1 is the mass of the water that is formed, and M is the mass of the organic compound that we have taken for the combustion, for burning in the combustion tube. And this 18 here is the what is the molar mass of water. In this case, it is the molar mass of carbon dioxide. 12 is for carbon, it is atomic mass of carbon 12. This is not this number. 100 is just for percentage. And here 2 is molar mass of hydrogen, which is H2. So 2 is the molar mass of H2. And then this numerical problem we saw. And then I have also explained that how one can estimate the presence of or the mass percentage of nitrogen. To estimate the mass percentage of nitrogen, there are two methods: Dumas method and Geldahl's method. Dumas method I have already explained. Geldahl's method I will explain today. So the Dumas method, what we have seen, organic compound which contains nitrogen when it is oxidized in presence of CuO, it forms carbon dioxide gas, water vapor, water gas steam, plus nitrogen gas, and some amount of reduced copper will be there. So now in this case, what do? We devise this reaction. This CO2 is now passing. You can see that in the furnace, the organic compound is burnt, and this organic compound actually forms nitrogen and other things. This is the KOH that we take into as the solution form. The CO2 is absorbed, even water is absorbed here in the KOH solution. Only the nitrogen out of the three gases, nitrogen that is formed, it will go above in this graduated tube. And what amount of nitrogen gas that is there from this in the graduated tube, the meter that is already there, we can find out the volume of the nitrogen. And from the volume of nitrogen, we detect the percentage of nitrogen that is present in the organic compound, nitrogen gas, N2 gas that is produced. So from that volume we can get, and considering nitrogen as uh, an ideal gas, we can apply the ideal gas equation. And the ideal gas equation, we know any gas at STP contains 22.4 liter volume. So it has a 22.4 liter volume, is 22,400 ml volume has. And so the what we can get for 1 mole of any gas, we can apply the ideal gas equation P1 V1 divided by T1 is equal to P2 V2 divided by T2. One condition we keep for the STP, and another condition we keep for the experimental condition is the temperature we take under, at what temperature this gas is collected here, and also at what temperature what pressure this gas is collected over here, and then the P1 V1 that we already and for the STP, the what is pressure and what is the temperature that is already know. Pressure will be 1 atmospheric pressure, 760 mmHg, and the temperature is 273 Kelvin. So for that condition is already known, and the volume that we also measure in the experiment. So P1 at what pressure it is collected in the experiment is known. P1 is measured, it is known. V1 is measured, it is known. Then but for the at the STP, the pressure, what is the value of pressure is already known. What is the value of temperature is already known. What is already now unknown is volume at the STP, and that volume we can calculate as volume at STP will be P1 V1, which is that experimental condition, P1 V1 by T1. And now the temperature at STP is, now you can see here in denominator it will get multiplied because here it was in denominator, and now the the temperature, and now the pressure will be in the denominator. I hope it is clear to you. Anyway, this I have explained. And once we get the volume of the nitrogen that is produced, we can also get other things. And with that, um, the, finally, what we get here is this: the percentage of nitrogen is 28 into V into 100 divided by this. This is the volume, and once you know the volume of the nitrogen that is produced at STP, and you divide this by the molar volume at STP, you get number of moles of nitrogen. And from the number of moles of nitrogen, you multiply the number of moles of nitrogen with the molar mass of nitrogen, which is 28. You will get the mass or the weight of the nitrogen that is produced. Once you know the weight of the nitrogen, and you also know the what amount of the amount of the sample that you have taken, and the mass of the nitrogen that is produced divided by mass of the sample you have taken into 100 will give you the mass percent of nitrogen. I think this is very clear to you. Only the thing is the nitrogen that is collected over here is to be that in the experiment that P1 should be atmospheric pressure minus 8%, because that nitrogen may also contain some of the vapor, and what is the pressure of the vapor that is already there mixed with the water, that should be reduced into something. Then let us now look into the Geldar's method, and then the Geldar's method, the organic compound is heated with the concentrated sulfuric acid. So this Gelal method is actually based on, there are three steps of this Gelal method. The first step is called digestion step. The second step is called distillation step, and the third step is called titration step. So the digestion step initially, and then distillation step, and finally it is the titration step. So there are three steps of this Gelal method, and the compound containing nitrogen is heated with the concentrated sulfuric acid. This step is called digestion step. So heating in a large flask, so there is a large flask, that is a specific type of flask. The organic compound will be put into it, and then concentrated sulfuric acid will be added in some amount of copper sulfate as well. And now this mixture will be heated. And once this mixture will be heated, what we see, the nitrogen in the compound gets converted to ammonium sulfate. So H2SO4 is there, nitrogen is now converted into ammonium sulfate, ammonia will be formed, and now that nitrogen will react with this hydrogen, ammonium sulfate will be formed. Now this ammonium sulfate, we take this mixture, and this mixture, acid mixture, this ammonium sulfate mixture, and heat it in the presence of an excess of sodium hydroxide. And once you take this ammonium sulfate solution and that mixture and heat it with the sodium hydroxide, the NH3 gas will be produced. And that step is here. The NH3 gas. You take this mixture and add NOH, enough amount of NOH. Ammonia gas will be produced. The ammonium sulfate will now be converted into ammonia gas. You can see the reaction here. The organic compound first is heated in presence of H2SO4 forming ammonium sulfate. Now ammonium sulfate when heated in the excess of NaOH, it forms sodium sulfate plus ammonia plus water. And this ammonia is now collected over into another flask which contains H2SO4, already contains a known volume and known molarity of H2SO4. And there is the excess of H2SO4, the higher sulfuric acid we also take in this step, third step. Now we take a known mass of H2SO, known amount of known volume and known molarity of H2SO4 into another beaker and collect this ammonia to passing through a condenser so that the temperature of ammonia goes down, and once the temperature goes down, solubility in H2SO4 will also increase, and will collect this ammonia into H2SO4 solution, and ammonia will react with H2SO4 to form ammonium sulfate again. So again, this ammonium sulfate, because this ammonium sulfate it also contains some other mixture of the compounds, and we cannot easily extract this ammonium sulfate. Since this the extraction or the separation of ammonium sulfate from this reaction mixture in the digestion state is difficult, so what we do, we first break this, dissociate this ammonium sulfate, we make certain reaction, the ammonia will be released. And only pure ammonia, since ammonia is the gas and this is the only gas that is produced here other than. So what we do, and the water is, although it is, then during the condensation state, you can see water will be condensed out, it will be taken on out and will be collected separately. Now, ammonia gas at the lower temperature only will pass into the H2SO4 solution and it will form ammonium sulfate. So pure ammonia now goes into this and to form ammonium sulfate, and now the only that is formed is ammonium sulfate, and there is no other thing that is formed here other than this neutralization. Now, so the ammonium sulfate is formed the solution of ammonium sulfate plus some amount of unreacted H2SO4. And that unreacted H2SO4 we can estimate in the third step, which we call as the titration state. And in the titration state unused H2SO4 will be neutralized with NaOH and uh, using using an indicator, and using an indicator this solution will be neutralized in presence of NaOH, taking NaOH into the burette, and this solution into the flask, and then we estimate, we find out what amount of NaOH is taken to neutralize unused amount of H2SO4. Some amount of H2SO4 will already be used to neutralize ammonia. Ammonia is basic, so it will already be used to form ammonium sulfate. However, since we are taking H2SO4 in excess and we are taking H2SO4 in excess, so that because we do not know exactly what amount of ammonia will be produced during this, because we don't know any estimation, quantitative estimation, idea of this ammonia or nitrogen that is present in the organic compound. We want to detect that, we want to determine that, and to determine that, so we take an excess of enough amount of H2SO4 solution so that all the ammonia that comes here, it forms in a ammonium sulfate, and the less amount, even if the H2SO4 is less in certain amount, we can find out what amount of H2SO4 was unreacted by titrating this mixture with sodium hydroxide. So the liberated ammonia gas is absorbed in excess of a standard sulfuric acid solution. The standard sulfuric acid solution we take in excess, and that ammonia will be absorbed. The amount of ammonia produced is determined by estimating the amount of sulfuric acid consumed in the reaction. So what amount of ammonia is produced, we can find out if we understand what amount of sulfuric acid is consumed in the formation of ammonium sulfate at this place. So that is what we can, and this we can find out what amount of sulfuric acid is consumed by estimating what amount of sulfuric acid is not consumed, unreacted. And with that we can, as I said, it is done by estimating unreacted sulfuric acid left after ammonia absorption by titrating it with a standard alkali solution in a standard NaOH solution. And so this is what we do here. So, the difference between the initial amount of acid taken and that left after the reaction gives the amount of acid reacted with the ammonia. And yes, so what we take this is what the reaction is again just written here. Organic compound plus H2SO4 ammonium sulfate. It forms ammonium sulfate. Ammonium sulfate when react with NaOH will form ammonia. Ammonia when react with H2SO4 into the at this place. The second ammonia is taken here. This will form ammonium sulfate. And now but we know let the mass of the organic compound taken as m gram. So the m mass of organic compound is taken taken initially, and let's just now the volume of the H2SO4 of molarity m is taken as V1. So what amount volume of H2SO4 we have taken in this state here at this place. We have also taken H2SO4 at this place, but we have nothing to do with what amount of the volume and normality of this H2SO4 here. Only we take H2SO4 that is taken to absorb ammonia, the volume, that is what only we are considering here. So the volume of H2SO4 of molarity n is let the volume molarity of the H2SO4 is m, and V1 is the volume that we have taken initially of the standard H2SO4 solution. Now, if the volume of NaOH of molarity n used for titration of excess of H2SO4 is V2m, so let us also consider the m just for the molarity of NaOH solution is also m. That is the same molarity of NaOH solution is same as the molarity of H2SO4. If it is so, and then V2 volume of NaOH is taken for for titrating excess of or the extra amount of H2SO4 means the unreacted H2SO4. Now what we know, the molarity of that this reaction happens in terms of a number of equivalents. So the number what we know, the one equivalent of H2SO4. So 1 mole of H2SO4 has two equivalents of H2SO4 because it is H2SO4. The valency factor here is 2. However, in case of NaOH, 1 mole of NaOH is one equivalent of NaOH, and thus the molarity of H2SO4, if it is n, thus the normality of H2SO4 will be 2 into m. Again, the valency factor is 2. However, in the case of NaOH, normality of NaOH will be equal to 1 into molarity, where 1 is the valence factor, because we know the cation has plus 1 charge or anion has minus 1 charge. In the case of H2SO4, anion has minus 2 charge, and two H plus cations are here. So the valence factor here is 2. So what does it mean? It means that if the molarity of both NaOH and H2SO4 are same, then in that case, what will happen, the NaOH, the volume of NaOH that is used, whatever the volume of NaOH that we have taken, that we have used for titration, only it will neutralize V2 divided by, if it is V2 of volume of NaOH we have taken, so it will neutralize only V2 by 2 ml of H2SO4, because Just a minute. Okay. So this is because in the case of H2SO4, we know the valency, as I said, the valency factor is 2, and in the case of NaOH, valency factor is 1. It means 1 molar NaOH is 1 normal NaOH, and 1 molar H2SO4 is 2 normal H2SO4. And 2 normal H2SO4 means the 2 equivalents of H2SO4. And what we know from the law of equivalence, one equivalent of acid reacts with only one equivalent of base. And since suppose 2m equivalents in the 1 liter H2SO4 solution, if we take, it is 2m number of equivalents will be there for H2SO4, and 2m will react with 2m of NaOH. And what we know, the normality of NaOH is just m because valence factor is 1. So actually it will react with double volume, twice of the volume of H2SO4 of NaOH will be taken as the H2SO volume of the H2SO4. And so what does it mean? Again, I'll just explain this. If the V2 is the volume of NaOH, just in simplicity, that is taken in the titration step, it means it has only neutralized V2 by 2 ml of H2SO4 of unreacted H2SO4. And it means the volume of unused H2SO4 will be what? It is V1 minus V2 by 2m. So V1 by V2, and this unused means at this step, V1 is the volume of H2SO4 that we have taken initially, and V2 by 2 ml of H2SO4 is used, is neutralized by NaOH. It means V1 by V2 by 2 ml of H2SO4 is consumed by ammonia. This simply means it is this volume that is consumed by ammonia to form ammonium sulfate. V2 by 2 is unreacted, it is now neutralized by NaOH, and now this is neutralized by NaOH. This is the initial total volume of H2SO4 we have taken. Now what does it mean? V1 minus V2 is the volume of H2SO4 that has actually reacted with ammonia originally to form ammonium sulfate. I hope it is clear to you. You have to understand and think a little bit here. Now the V1 by minus V2 by 2, this ml of H2SO4 of molarity M is what is used by ammonia to form ammonium sulfate. And to find out the volume of ammonia solution, what we will have to do again in the case of ammonia, the valency factor is 1. Why it is 1? Because 1 ammonia reacts with 1 mole of ammonia reacts with only half mole of H2SO4. You can see here 2 moles of ammonia is required to react with 1 mole of H2SO4. It means 1 mole of ammonia reacts with only half mole of H2SO4. So again, what we see, the volume of ammonia that is required to react with the volume of H2SO4 will be twice of the volume of H2SO4 that we have taken. If the molarity of the ammonia and H2SO4 solutions are same. If their molarity will be different, the calculation will be a bit more tricky. That is even not difficult. But here is we have just considered it in for your understanding all the molarity for NaOH, H2SO4, and even for ammonia in, just to make this thing easy. So what does it mean? If the V1 minus V2 by 2 ml of H2SO4 of molarity in reacts with ammonia, it means it will react with 2 into, twice the volume of H2SO4, 2 into V1 minus V2 by 2 ml of ammonia solution of molarity. Now this is the what the ammonia volume of ammonia solution we know. Ammonia solution is if the ammonia is dissolved in water, it will form NH4O. And this NH4, which one can see, it will react with H2SO4 to form ammonium sulfate plus water. So what one can do, the molarity is what I have written here is molarity of ammonia we have considered in. We do not know what molarity of ammonia is there in the ammonia solution is there. What is the molarity? Now what we know from the definition of molarity is, molarity means the number of moles of a given substance in 1 liter of the solution. It means 1 liter of the solution means 1000 ml of the solution. And what does it mean? If the 1 molar M molarity means M mole of that substance is dissolved. If the solution is 1 molar, it means 1 mole of that substance is dissolved. So 1 molar ammonia solution means 1000 ml of 1 molar ammonia solution contains what? 1 mole of ammonia, and 1 mole of ammonia is 17 gram. This is what the molar mass of ammonia in gram. 1 mole of ammonia means 1 into molar mass of ammonia in gram will give us the number of the amount of ammonia in gram. The molar mass of ammonia is 17 gram per mole. The nitrogen mass number 17, hydrogen 1, so 3 into 1 plus nitrogen, sorry, 14, nitrogen 14 plus 1 into 3, 3 hydrogen atoms are there, it will become 17. So it will contain 17 gram of ammonia. Or if, because we are focusing here on just the amount of nitrogen, so the 17 gram of ammonia will contain 14 gram of nitrogen. Or another way of understanding this is 1 mole of ammonia contains 1 mole of nitrogen, and 1 mole of nitrogen is molar of mass of nitrogen in gram, and molar mass of nitrogen in gram is what? The mass number of the average atomic mass of nitrogen in the unit just change from atomic unit to just take it into the gram is what the molar mass of nitrogen in gram will be. So what we see, the 1000 ml of 1 molar ammonia contains 14 gram of nitrogen. Therefore, 1000 ml of m molar ammonia solution will contain 1 molar 14 gram m molar of the same volume will contain 14 into m gram of nitrogen. So 14 into m gram of nitrogen is there into the 1000 ml of ammonia. So 1000 ml of m molar ammonia solution contains 14 into capital M molar, 14 into capital M gram of nitrogen. And but this is the actual volume of ammonia that is produced that the, in the second step. And the second step, it means this step, the distillation step. So the what we know, so this much volume, so 1 ml of m molar ammonia solution will contain 14 m divided by 1000 ml divided by 1000 gram of nitrogen. So 2 into V1 minus V2 divided by 2 ml of ammonia solution will contain 14 into molar mass of nitrogen is 14 m divided by 1000, this 1000 into this volume 2 into V1 minus V2 divided by 2. This is the amount of nitrogen present in the nitrogen in the gram that is present in the sample. And once you know the amount of nitrogen in the gram, and if you also know, you initially measured, if you initially weigh the amount of the organic compound that you have taken for for determining the percentage mass of nitrogen, to divide that the mass of organic compound from the mass of nitrogen, and then multiply the entire thing with the 100 to give the percentage of nitrogen. I think this is a very standard thing that we do for every for the for calculating percentage of anything. And so on solving this, what we get the 100, these two zeros and two zeros will cancel out these two zeros. So and this is means this 100 is 1000 in 10 times of 100, so 10 is here, and that 10 will make it 1.4. So we get 1.4 m into 2 v1 minus v2 by 2 divided by m, where here m is here m is the mass of the sample that we have taken. V1 is the initial volume of H2SO, a standard H2SO4 solution that we have taken. V2 is the volume of NaOH that we have taken during the titration, means the volume of NaOH used for titration to find out the end point of the titration. M is the molarity of the solution, whether it is ammonia, because all the molarity that we have already considered are has the same value, ammonia and NaOH as well as H2SO4. The M is the molarity. So with that we get this volume, and sometimes what happens is this entire value is given. So this much amount of ammonia is given, this much volume of ammonia solution is formed. So you can directly use this equation in place of this, the volume of ammonia will put. Let us see this. So please note here that the Jalal method does not apply to compounds containing nitrogen in nitro azo groups or the nitrogen present in the ring. So if the nitrogen is present as a nitro group or the azo group or the nitrogen present in the ring, if this Jalal method will be ineffective, it will not give us the correct measure of the percentage of nitrogen present in the organic compound. and this is because these compounds does not change to ammonia sulfate under the given these conditions. The conditions that we have used, the H2SO4 and CuSO4, when we add, we heat, the ammonia that will be formed, this ammonium sulfate will be formed, and so on. So under these conditions, the nitro compounds or azo compounds do not give this taste or the Jellal taste, and so we do not use Jellal method if the nitrogen present in the compound is in the ring or in the form of a nitro compound. Let us now see this numerical problem. During estimation of nitrogen present in an organic compound by Geldahl's method, the ammonia evolved from 0.5 gram of the compound in Geldahl's estimation of nitrogen. So this is the amount of the compound that we have taken initially measured before we started the estimation of nitrogen. Now what we do with to this compound H2SO4, CuSO4 will be added and this experiment, then it will be heated ammonium sulfate will be formed. This ammonium sulfate in the next distillation state will be treated with NaOH. Excess of NaOH ammonia gas will be produced, which will be collected in the excess of standard H2SO4, and then the volume of H2SO4 that we have taken, as well as the volume of NaOH that we use for the neutralization of non-reacted H2SO4 will give us, with that we get this equation. So anyway, now let's see the other part of the question. And this neutralized ammonia that is formed evolved in it neutralized 10 ml of 1 molar H2SO4. It means the amount of H2SO4 that has been used for neutralization of ammonia directly is given. There the volume of NaOH is not given. What does it mean? It means this V1 minus V2 by 2 is given. V1 minus V2 by 2, it gives us what? V1 minus V2 by 2, it gives us the volume of H2SO4 that reacts with ammonia. This V1 minus V2 by 2 ml of H2SO4 which reacts with ammonia. And this, if it is given, the volume of H2SO4 reacts with ammonia. So it means it has given V1 minus V2 by 2, this value in parentheses. And 2 is just for the valency factor that we see for the H2SO4. And so it means the 2 times of the ammonia, the number of moles of ammonia will be used, uh, 2 times of the number of moles of ammonia will be used as the number of moles of the H2SO4, and that we see as per this equation. For 1 mole of H2SO4, 2 moles of ammonia is used. So that is what we see. So another way to solve is 1 molar of H2 of 10 ml H2SO4 means 1 molar of 20 ml ammonia. This is what the equivalent, because 1 molar 10 ml H2SO4 will have 2 into 10, 2 into 10, 20 milli equivalents of H2SO4. And 1 molar of 20 ml ammonia will have 1 into 20 milli equivalents of ammonia. So the number of equivalents of milli equivalents will be equal. So we have to multiply this with 2 just because we have to multiply this with the valency factor. Either we could do, if you take just 2 molar of ammonia, if the ammonia was 2 molar, then again the volume of H2SO4 and volume of ammonia taken will be equal to 0. That will be equal. But if the same molarity of ammonia and H2SO4 are there, it means the volume of H2SO4 will be uh, just half of the volume of ammonia that is reacted with this H2SO4. So anyway, what we see now that the 20 ml ammonia solution is considered this 2 into V1 minus V2 by 2. This value 2 into V1 minus V2 by 2 ml of ammonia solution. Or otherwise, what you can do is just use this equation 1.4 into 10 molarity is I think given already. 1 molar H2SO4 is given. So molarity of H2SO4 is 1 into 2 into this. 2 you can write V1 minus V2 by 2 is 10 divided by mass of the substance in grams. So 1.4 into 1 into 2 into 10 divided by 0.5 into 100 will give us the percentage of nitrogen present in the organic compound. So 14 into 1 into 2 into 10, or you can directly from this equality take 20 ml, and this 20 ml will correspond to this value from here to here. One is molarity, 14 is what we already know here in this equation, divided by 1000, you can see the 3000 here, into 100 by n, into 100 are divided by n is the amount of substance that we have taken organic compound. And this will give us 56.0% nitrogen is there in the organic compound. Let us now look into the estimation of halogen quantitative estimation of halogen atoms. And here we use the Carius method. And in the Carius method, we take a Carius tube, and this is what is called the Carius tube. It's a filled capillary tube. Actually, it ends at here, the filled capillary at the end. This Carius method, the known mass of the organic compound is heated with the fuming nitric acid in this Carius method to estimate the nitrogen or the percentage of halogen atoms present in the organic compound. So the organic compound, the known mass, will measure the mass and then weigh the mass and note it down, and then we add to the that compound to the carrier tube, and then we add fuming nitric acid to that compound in the presence of silver nitrate, and we also add silver nitrate contained in the hard glass tube known as carrier tube in a furnace. And this carrier tube is put into the furnace, and so it will be. So carbon and hydrogen present in the compound are oxidized to carbon dioxide and water. The halogen present forms the corresponding silver halide. So carbon dioxide and water will be evaporated, carbon and hydrogen will go away. Now the halide that is present in the organic compound, since we are also adding this carries to silver nitrate, and this silver nitrate will react with the halide to form silver halide, and silver nitrogen and silver ion react with halide to form silver halide, and it is filtered. The silver halide will be formed as a precipitate, which will be filtered, washed, and dried and weighed. Once we weigh the silver halide, mass of the silver halide, 1 mole of the silver halide contains 1 mole of the halogen atom, and so is the M is the mass of the organic compound in the gram, and the mass of AgX formed is M1. The AgX precipitate that is formed, that is weighed after the drying filtration and drying is M1 gram. So what we know, 1 mole of AgX contains 1 mole of X. It means molar mass of AgX will contain 1 molar mass of X. And this simply means AgX molar mass of, suppose molar mass of AgX silver halide is M, and molar mass of X is A. So what we get, 1 mole of so M gram of AgX contains A gram of X, and therefore 1 gram of AgX contains X divided, so A divided by M gram of X, and thus M1 gram of AgX, because we have just M1 gram of AgX is formed, which is what we have read. So M1 gram of AgX will contain A divided by M. A is the molar mass of X, which is nothing but average atomic mass of X, and divided by molar mass, which is the molar mass of AgX, which is M. So A divided by M is M1. So what we write actually is atomic mass of X divided by molecular mass of AgX into M1 gram. A divided by M into M1 gram is the mass of halogen present in this organic compound, and that halogen present in this AgX as well. The same amount is present in AgX as well. So the percentage of halogen will be equal to atomic mass of X is what the entire thing divided by mass of the organic compound that is taken originally into 100. With that we get the percentage of halogen. And you can see here the 50 centimeters long the carrier tube, which is put into the furnace, and then contains AgNO3 here. The organic compound is added here, and the fuming is mixed, and it forms as the finally the halide is there, AgX, and estimating the AgX we estimate the percentage of halogen. Let us now see this question. In a carrier method of estimation of halogen, 0.1 gram of an organic compound gives 0.12 gram of AgPr. Find out the percentage of bromine in the compound. So AgPr that is produced is 0.12 gram and the amount of organic compound that we have taken is 0.15 gram. Just so what we can calculate from this AgBr, this is the molecular formula of the silver halide, and this is silver bromide, and silver bromide molar mass will be equal to atomic average atomic mass of silver plus average atomic mass of bromine, 108 plus 80 will be equal to 188 gram per mole, and 188 gram per mole silver bromide means it contains how many gram of bromine? It contains 18 gram of bromine that we have added here as you can see. So 188 gram of silver bromide contains 80 gram of bromine. Therefore, 1 gram of silver bromide contains 80 divided by 188 gram of bromine, and thus 0.12 gram of silver bromide, which we obtained from this organic compound. So 0.12 gram of AgBr will contain 80 divided by 188 into 0.12 gram of bromine. And the percentage of bromine, once we know the mass of bromine and also know the mass of the organic compound, then we can get the percentage of the bromine present in the compound. So this is the mass of the bromine divided by this divided by mass of the organic compound into 100 is what we get. So this is 34.04% we obtained for this case. Let us now see how one can estimate the sulfur. The method to estimate the sulfur present in the organic compound. Here again in this case as well, we use carrier tube, but and also we use fuming HNO3. But in place of AgNO3 here we use sodium peroxide or sorry, we don't use sodium peroxide or the fuming nitric acid. So in the carrier tube other than the organic compound, no mass of the organic compound, you can simply adjust HNO3, fuming HNO3 and we see this reaction and then later on in the presence of AgNO3 that we have taken in the detection of halides, we add here barium chloride. And so what will happen as we show in the case of the halogen, halides are formed. In the case of the sulfur, if it is present in the organic compound, sulfide will be formed. And that sulfide when reacts with the barium chloride, it will form barium sulfate because it is a solution. So a known mass of organic compound is heated in a furious tube with sodium peroxide or fuming nitric acid, and the nitric acid oxygen is also there. And sulfur in the compound is oxidized to sulfuric acid, not sulfide. Sulfide is mistake. So it will be converted into the sulfuric acid, and once the sulfuric acid that is formed because of the oxidation of the organic compound containing sulfur, when reacts with the barium chloride, when barium chloride is added to this digestible barium chloride solution in water, it forms barium sulfate, and barium sulfate forms precipitate. It is not soluble in water, and so this precipitate we can filter it out, dry it out, weigh it, and from the weight of the barium sulfate that is formed, we can estimate what amount of the sulfur was present in the compound, considering all the amount of the sulfur, all the atoms of the sulfur in the given sample of the organic compound has converted, it has gone to form barium sulfate. This is what one assumption is. Here, no amount, not even a single atom of sulfur is lost in evaporation or any other process. So the precipitate is filtered, washed, dried, and weighed. The percentage of sulfur can be calculated from the mass of barium sulfate. Let the mass of the organic compound taken is 1 gram and the mass of barium sulfate is 1 gram. 1 mole of, now we know 1 mole of barium sulfate is equal to the molar mass of barium sulfate, and the molar mass of barium sulfate you can calculate it will be 233 gram barium sulfate. And this 233 gram, 1 mole of barium sulfate contains 1 mole of sulfur, and so 233 gram, 1 mole barium sulfate means 233 gram of sulfate, barium sulfate contains 1 atom of sulfur means 32 gram sulfur. So 233 gram barium sulfate contains 32 gram sulfur. Therefore, m1 gram of barium sulfate will contain 32 divided by 233 into m1 gram of sulfur. And so the amount of sulfur that is there in the barium sulfate or the indirectly organic compound is obtained here, and from here we can get the percentage of sulfur. So atomic mass of sulfur, we see this atomic mass of sulfur divided by molecular or the molar mass of barium sulfate into m1 gram, and m1 here is the mass of BSO4, the precipitate that is obtained, into 100 divided by n, which is the mass of the organic compound that is there. So from here we can calculate the percentage of sulfur, or this equation we can also directly use 32 m1 divided by 233 into 100 by n. So this we get 32 into m1 divided by 233 into 100 by n percent is the percentage of sulfur. Now let us see this question. In the sulfur estimation, 0.157 gram of an 0.157 gram of an organic compound gave 0.4813 gram of barium sulfate. What is the percentage of sulfur in the compound? So we have to find out the percentage of sulfur in the compound. This is the amount of the barium sulfate that is obtained, and this is the amount of the organic compound that is taken. So what we see, this amount of the barium sulfate means M1, the value of M1 is already given in this equation, percentage of sulfur. Also, the value of M is given as 0.157 gram. So the molecular mass of barium sulfate will be 137 is the average atomic mass of barium, or the mass number of barium. Sulfur is 32 and 4 oxygen is 4 into 16, 64. So we get 233. 233 gram of barium sulfate contains 32 gram of sulfur. So 0.4813 gram of barium sulfate contains 32 divided by 233, 4 into 0.4813. 32 divided by 233 into this number gram of sulfur, and the percentage of sulfur will be 32 into this 0.4813 divided by 233 into 100, because the percentage divided by mass of the organic compound 0.157, this gives us 42.1%. And 42.1%, we can also directly just apply this equation. We can remember this equation, apply this equation, just choose the values of M1 and N, which is already given in the question, and we will get the percentage of sulfur very easily. Now let us look into the estimation of phosphorus. So earlier, like we have seen phosphorus, to detect the phosphorus event in the qualitative analysis, we first oxidize phosphorus, and after oxidizing phosphorus, you can see here, using sodium peroxide, it is oxidized into phosphate, and this phosphate will react with HNO3 forms phosphoric acid, and this phosphoric acid will react with ammonium molecule and HNO3 nitric acid from ammonium phosphate molecule, which is the precipitate to separate it out, wash it, dry it, weigh it, and you see the amount of ammonium, the amount of ammonium phosphate is there. And let us go back where we were. Yes, now. So known mass of estimate the amount of phosphorus, or to estimate the percentage of phosphorus present in the organic compound. The known mass of organic compound. Again, in each case, the known mass of organic compound is taken. We have to measure the mass of the organic compound, because if you do not know what amount of organic compound is taken initially, you cannot find out the percentage of an element present in that organic compound. So a known mass of organic compound is human nitric acid. After which phosphorus present in the compound is oxidized to phosphoric acid, and then the phosphorus is oxidized to phosphoric acid, and this phosphoric acid is precipitated as ammonium phosphomolecule, NH4 by adding ammonia and ammonia molecule. So ammonium molybdate and ammonia to a phosphoric acid solution to get the formation of ammonium phosphomolybdate. Alternatively, not this, we can take another precipitate we can also be found. So alternatively, phosphoric acid may be precipitated by ammonium by magnesium ammonium phosphate. This magnesium ammonium phosphate will take and it will also precipitate. So, sorry, phosphoric acid will also be precipitated if you add magnesium solution. Magnesium is MgOH white solution and ammonia. So it will be precipitated and MgOH white solution with ammonia if you add to the phosphoric acid solution that is formed after the oxidation of the organic compound containing phosphorus, you will see the formation of magnesium on ammonium phosphate, which on ignition yields Mg2P2O7. This compound is not very stable, so Mg2P2O7 is stable, and from the what amount of Mg2P2O7 is formed, from that you can find out the percentage of nitrogen as well. Let us now see first the formation of ammonium phosphomolybdate. The molar mass of ammonium phosphomolybdate will be 1877 grams. You can just find it out, just calculate it. It will be 1877 grams. The percentage of phosphorus will be, what does mean? This 1877 grams of ammonium phosphomolybdate contains only 31 grams of phosphate, as you can see here. Because 1 mole of this ammonium phosphomolybdate contains only 1 mole of phosphorus. So 1877 grams of ammonium phosphomolybdate will contain only 31 grams phosphorus. And so percentage of phosphorus one can calculate as this 31 gram, 1 gram of ammonium phosphomolybdate will contain 31 divided by 1877 grams. And if the M1 is the mass of the ammonium molecule that is formed, so we can find out the total mass of phosphorus that is present in the ammonium phosphomolybdate, and it will be 31 divided by 1877 into M1. And now you divide this value with the mass of organic compound, and that with the resultant value multiply with 100, you will get the percentage of phosphorus present in the organic compound. So this 31 divided by 1877, that is already know here, into M1. M1 is the mass of the phosphomolybdate that is formed and calculated out. M is the mass of the organic compound, and thus the percentage of phosphorus would be 62 into. Sorry, this is what. If the phosphorus is estimated in the form of Mg2P2O7, then in that case, what happens? 1 mole of Mg2P2O7 contains 2 moles of phosphorus, and the mass of Mg2P2O7 is also small, and the molar mass of this Mg2P2O7 is 2.2 gram per mole. So in the place of this 31, we will have to write 2 into 31 because it's 2 moles of phosphorus is there in this compound, and 2 into 31 is 62 into M1. M1 is the mass of this Mg2P2O7 divided by this molar mass of Mg2P2O7, and we will give the total mass of the phosphorus present in the organic compound and divide that mass with the M and multiply with 100, and we get the percentage of phosphorus present in the organic compound. And here in this equation, the last equation is what you can see here. 222 U is the molar mass of Mg2P2O7. M, this M is the mass of the organic compound taken. M1 is the mass of Mg2P2O7 formed. And 62, this 62 is the mass of 2 phosphorus atoms present in the compound Mg2P2O7. And this is how we also estimate, this is how we estimate phosphorus present in an organic compound. Let us now see how one can estimate the presence of oxygen as well, or the percentage of oxygen in the given organic compound. The easiest way is you get the to percentage of all the other elements present in the organic compound to sum of the percentage of all the elements, mass percentage of all the elements present in the organic compound and subtract it with the 100%, that is the total percentage of all the organic percentage of the mass percentage of all the organic compounds, and what we get is 100, and the 100 minus the sum of the mass percentages of all the organic compounds will give us the mass percentage of oxygen present in the organic compound. The percentage of oxygen in an organic compound is usually found by the difference between the total percentage composition, and the total percentage composition will be 100 because the sum of the percentage compositions of all the elements you will get is 100, and sum of the percentage compositions of all the other compounds, all the other elements present in the organic compounds, and all the other elements how we can get the mass percentage we have already discussed. So that way is the one way you can obtain the mass percentage of oxygen. However, you can also obtain the mass percentage of oxygen di- directly using some other technique, some other method. So a definite mass of one of the method is a definite mass of an organic compound is decomposed by heating a stream of nitrogen. So a stream of nitrogen is used to heat the known mass of an organic compound. A mixture of the gaseous products containing oxygen, which will this mixture of the gaseous products that we produce, it will contain oxygen and which is passed over a red hot stove, and when this oxygen is passed over red hot coke, it will react with the carbon present in the coke, that is cooking nothing but carbon. It will react with the carbon and here because it passed over the red hot coke, that in the absence of it, the in the deficiency of oxygen, it will form carbon monoxide. And all the oxygen is now converted to carbon monoxide. The carbon monoxide, the mixture is passed through the warm iodine penta iodide. So, when this mixture of the gets passed through warm iodine pentoxide, iodine this is I2O5 is iodine pentoxide, then carbon monoxide is now here is oxidized by iodine pentoxide to carbon dioxide and produces iodine, and it also produces iodine. So this oxidizes carbon monoxide to CO2 and reduces itself to form iodine, because iodine here is in plus 5 into 2, it is to plus 5 oxidation state. So if you get reduced, it will, if it produces iodine, or if iodine is produced in this step of the reaction. So what we see, the compound, the known amount of the compound is heated, and the oxygen gas will be produced plus other gaseous products that will also be formed. This oxygen, when it is passed over the coke, red hot coke, so you can see the temperature, it will form carbon monoxide, and when this carbon monoxide is oxidized by iodine pentoxide, it will form iodine plus uh, elemental iodine plus CO2. If we multiply this with 5 and this with 2, we can make this reaction balance as well. So that this 2 into 5 is 10 molecules of CO will be there in product, and if the 5 into 2 is multiplied with 2, 10 moles of CO will present in the reactant, this will be cancelled out. So we can further say. So by making the amount of carbon monoxide produced in equation 1 this equal to the amount of CO used in equation 2, by multiplying the equation 1 by 5, you have to multiply this equation by 5 and equation 2 by 2, as you can see here. Respectively, we find that each mole of oxygen liberated from the compound will produce 2 moles of carbon dioxide. So even during this reaction, what we see, each mole of oxygen forms 2 moles of carbon monoxide, and this because the second oxygenation in the formation of carbon dioxide from carbon monoxide is coming from iodine pentoxide. So thus what we know, 1 mole of oxygen produces 2 moles of carbon dioxide ultimately. And 2 moles of carbon dioxide means 2 into molar mass of carbon dioxide means to put 4 into 2, 88 gram of carbon dioxide is produced from 1 mole of oxygen on 1 mole of oxygen gas O2 gas is 32 grams. 2 into 60 gram of oxygen. So 88 gram of carbon dioxide is obtained, and this carbon dioxide one can measure the mass of this carbon dioxide, as you know, if you collect it over KOH solution and all. So if you know the mass of the CO2 produced, so one we can calculate the mass percentage of oxygen directly as well. So thus 88 gram of carbon dioxide is obtained in 32 gram of oxygen is liberated from the organic compound. And if this is liberated from the organic compound, then just give me a minute. Yes. So 1 gram of carbon dioxide is obtained by 32 divided by 80 gram, 88 gram of carbon dioxide, and thus m1 gram of carbon dioxide will be obtained from 32 gram divided by 88 gram into m1 gram of oxygen will be produced. And so the M1 from M1 gram of carbon dioxide 32 divided by 88 into M1 gram of oxygen will be produced. And thus the percentage of oxygen will be mass of oxygen divided by mass of the organic compound in percentage. And that's how we get the percentage of oxygen directly using this experimental technique from the given amount of organic compound. And the percentage of oxygen can also be derived from the amount of iodine produced. Not only the CO2, we can also derive the percentage of oxygen from the amount of iodine present. You just have to understand what is the chemical reaction that is happening, and so we can also do that. Nowadays, estimation of elements in an organic compound is carried out using micro quantities of substances. We don't want to waste the organic compound or something. We just take very small amount of substances, and automatic experimental techniques are already present. And the elements carbon, hydrogen, and nitrogen present in a compound are determined by an apparatus known as CHN elemental analyzer. The CHN elemental analyzer, and the analyzer requires only a minimal amount of the substance, that is just between 1 to 3 milligrams, and displays the values on the mass percentage of all the elements that are present, with all the elements of carbon, hydrogen, and nitrogen present in a compound on the screen. It will display in a very short time. And what the detailed discussion of this is not in our syllabus, it's beyond the syllabus. And so we will not study any further about this. And this is how where this chapter is over. So all the basic concepts of organic chemistry we have already studied. The nomenclature of organic compounds we have seen. We have also seen the general naming and the names of the different substituents or the branches that are there in the organic compounds, all the functional groups that are there into the organic compounds we have already seen, and what are their structures as well. We have also seen isomerism, the basically two types of isomerism, structural and stereoisomerism. The structural, four types of structural isomerism, and two types of stereoisomers, optical and stereo we have already studied. Then we move to some other important concepts and different effects. The electron movement effects in the organic compounds we have already seen. The heterogeneous, homogeneous, for, heterolytic and homolytic cleavages we have studied. Plus I effect, minus I effect, or the inductive effect, which could be plus I or minus I. Then resonance effect, electromeric effect, um, hyperconjugation, many other effects we have already studied. Then we also studied the qualitative estimation of organic compounds, and then quantitative estimations of or estimation of organic compounds. Other than that, we have also seen the separation techniques that we use to purify organic compounds or to mm, those things. So almost all the basic things that we cover that is important to understand chemical reactions and other things is covered in this chapter. I'll start a new chapter. This chapter is over. A new chapter afresh. Next lecture, next class.